Slide 1, waiting line theory. Waiting line theory. We're only going to cover these 4. Right? Poisson arrivals, exponential service, single channel. This means, there could be, like, I'm going to keep using Baker Credit Union as an example, and only one teller's working. People arrive, they get in line, but when the teller's free, they walk up and get service. Single channel. Anyway, these are all Poisson arrivals, and then these are the services, and these are separate. So you have 1, 2, 3, 4, 5, 6, 7 subjects. There's more stuff we'll talk about, but these are the 7 important subjects. And the deal is, Monday, however far we get, could be on the final. If any of these 7 are not covered by Wednesday, it won't be on. It won't be on the quiz. I meant to say not final. So anything that's not covered, if we don't get it far enough to get these 2, for example, they won't be on the quiz. We'll cover them after the quiz, then they'll be on the final. So however far we get. I don't want to go too fast because I start to lose people here a little bit. I figured out a way to kind of make this easy. But it used to be 3 lectures because a lot of students were like, oh, what do you do? This is too much. Here we go. These are the 4 subjects. The number 1 mistake that people make when they're working on these is identifying which one of the 4 that they're reading about. That's the number 1 mistake. So when you're reading a problem, I'm going to give you some things to look for to quickly identify which one of these 4. And this is the easiest one. A problem that's talking about arbitrary service always includes a standard deviation as part of the description of the service. It's the only one that will have a standard deviation in there. And right away, if you see the standard deviation, you go, this is arbitrary service, and you jump to that page or slide to look at those formulas. There's about 6 formulas for each one of these. They're different formulas, but they're calculating the same 6 items that you could be asked about, which we're going to talk about. So, the problem that describes service includes a standard deviation. That's arbitrary. Now this one, exponential service multi-channel, of the 4 we're learning, is the only one that will be multi-channel. So as you're reading the description, if it says there's 2 tellers, or 3 tellers, or 2 cashiers, or 3 ticket takers, or 5 ticket takers, any more than 1 channel providing service, you know it's got to be this one, because it's the only one we're going to learn that is multi-channel. There's other ones that are multi-channel, but for our class this semester, this is the only one we're learning. So that should be easy to identify. Arbitrary should be easy, multi-channel should be easy. Constant service. This is kind of harder to identify, but this is what you ask yourself when you're reading about the service. Usually there won't be a human involved, and that's how it becomes constant. For example, you drive up to a single car wash. It only has 1 type of car wash. You have to put the money in, you pull up, you stop, and the thing works around you. If it only provides 1 type of car wash, the service will be the same for every car that goes in there. That's called constant service because there's no humans involved to affect the amount of time it can take. And there's no options other than 1, wash my car. Another example I used to use is going back a long ways. Old coffee machines, when you go to get a coffee, you push the button, there's 1 option, coffee. And you push it, and the cup drops down, and you hear some hotness taking place and something boiling, and all of a sudden coffee's pouring in. Whoever walks up, the same amount of time to provide the service of getting that coffee is the same amount of time for every single person. That's constant. And you notice each one I described didn't have a human involved. That's usually the case in constant service. And when you recognize that, you know it's this one. So arbitrary has a standard deviation. Constant means most likely there isn't a human involved. It's the same amount of time. The description even talks about every person that gets served is this amount of time. It means the same amount of time for each person. The example on the PowerPoint, one more. There's that mechanical horse in the front of the store in our example in the PowerPoint. And if a kid walks up and puts 50 cents in, they get a 2-minute ride. No matter what, it's a 2-minute ride for every single child that puts the 50 cents. That's constant service. Now here's one that's very hard. Poisson arrivals, exponential service, single channel. You say to yourself, is that constant? No. Is it half standard deviation? No. Is there more than one channel? No. It's got to be this one. That's how you figure this one out. That's the fastest way. Everybody hear that? Process of elimination. I realize it's not constant because there's humans doing it and whatever, and it's only talking about one service channel, and there's no standard deviation in the description of the service. This is all select. Exponential service, single channel. Okay? So there's the four, and now you have the hints to try to recognize which one of these four you might be reading about in a problem. This section of our lesson is just figuring out how to calculate the probabilities of arrivals only. There's nothing about service even in the question. It's asking about arrivals only. And then this one called exponential service probabilities, this is just like the other one, but it's asking about service only and the probability of service taking place this way or that. So these are just like straight from stats, these two. So I may, and people get these confused with these because these have probabilities also, but these include both arrival and service as part of the whole thing. This one, Poisson arrival probabilities, are just about arrivals. And this one, exponential service probabilities, are just about service only. Now this last subject, economic analysis, is the most important part of the whole chapter. There will for sure be at least one or two economic analysis calculations in your future, if it's not quiz 6, or it could be both quiz 4, not quiz 6. Quiz 4 or the final exam, it could be both. That's how important this part is right here. Because this is truly how you make the best decision. You take the information from here and you calculate what you need to calculate, and then you plug it into this economic analysis to say, let me give you an example. You're the one who's going to hire the person doing that job right over there. And it's a waiting line job. Let's say you're hiring tellers. But you got it down to 2 really good applicants. And you don't know which one to hire. All right? So you're going to figure it out by having both of them do the job and do a little time study to see what their average service time is. You know, they're supervised. They're just kind of, they're not actually doing the job. Maybe even role-playing. A lot of role-playing business, which I hate the most, but it happens. So you do that, and you get a time study, and then the other applicant comes in, and at the end of their interview, you might do a time study on them. As long as you know the average time they'll take to help customers, you already know the rate at which customers are coming in because you've been open for years. If you can get the rate that they could service customers, you can calculate which one with economically analysis would be the best hire. For example, one of the applicants could be, $16 an hour, and they are kind of average in speed. This other one is going to be like $20 an hour, but they're much faster because of their experience already at another credit union. So you do an economic analysis to figure out, is it worth the extra money for the increased speed of service that could take place based on the average amount of customers we have arriving during this particular shift or whatever's going on. You get it? Now, did I just describe a single channel and multi-channel problem that you would then figure this all out with? Single channel, but notice I talked about 2 different people. Only one would be working at a time. If I said you're trying to figure out if you should have both of them work or only one of them work, now we're comparing single channel to multi-channel. But I said you're trying to figure out which one to hire and only one of them is going to be working. That's a single channel problem, so I don't want you to confuse that. You get it? Multi-channel, the question's going to be about, you're trying to decide whether you should have 3 tellers during this particular shift based on the amount of customers that arrive usually, or 4 tellers. You'll do an economic analysis based on 3 tellers, and then you do it again for 4 tellers, and it will tell you what would be the best decision there. As long as you're staying within a certain probability of a person having to wait too long. That's what you're calculating. You want to know, what's the probability a customer's going to have to wait too long and we're going to have poor goodwill? There's cost when a customer starts to get upset for waiting too long. And it's not just possibly the loss of sale if something's being sold, but it's the goodwill. Companies like the Secretary of State has no competition, I mean, other than another Secretary of State. And so their tolerance calculation as to how many people should be helping customers at Secretary of State is not necessarily based on the probability of how many customers have to wait and if they'll get upset. Because they don't care, only because there's no competition to force that motivation of caring. You know, there's no competition. We have to. We all have to go to the Secretary of State for that particular business, and we have no choice. I mean, if we drive to another Secretary of State, but they're the same company. But your local hardware store, they have tons, or how about your auto supply? Your auto supply store. You know, you got AutoZone, you got, I can't think of it, but you got how many now in town? They're all over. There's three just on Bristol Road within a 2-mile stretch. So they have to calculate all this, you know, if they're big enough to calculate, to keep the probability of a customer getting upset and waiting too long low. Now, in real business, all what I just described to you is how you calculate what the cost would be if a customer has to wait too long. That's the hard part. Because this economic analysis takes the cost to have of the employee providing the service and the cost if we're not providing the service fast enough, called the waiting cost. For this class, you'll be given the waiting cost and you'll be given the cost per channel. But in real life, that waiting cost is the hardest part of it. You know, that's, again, meeting after meeting. You know. How much would the average customer spend? If they go down the road and spend it, will they come back? Will they never come back? You got all of that to take into consideration. At which point will they never come back if they wait so long? So, I'm jumping to a formula on slide. I gotta find it. I can't find it. I just know it when I see it. Oh, I know. I forgot. I put together this example. Here we go. Okay, economic analysis down here. In this example that I'll post, and we'll talk about more, here's the economic analysis portion. All of that up there was once you discovered which one of these 4 that problem was, you started calculating some of those 6 calculations you got to do that we're going to talk about. Well, after you're done with that, you jump into the economic analysis, which isn't that hard once you get those numbers. You ready? I'm going to go to the story. We're coming back. Here's the story. You're trying to decide as a manager whether you should have 2 or 3 channels of service open. Should I schedule 2 employees for this particular shift or 3? It says the arrival rate, let me emphasize this is rate, compared to time. Very different from each other versus time. It says the arrival rate is equal to 2.5 customers per hour. And the mean, the average service time per channel equals 10 minutes. This says 10 minutes. That's in time. You have to use rates for both the arrival and the service to do your calculation. There are ways to do it with time. It's much easier if you, any question that gives you either the arrival or the service in time, to convert it to the rate per unit of time that's the same as the arrival and service. Right? Arrival and service have to be how many per same unit of time. You can't stray. Now, arrivals are already per hour. So we got to convert service. The easiest way would make that per hour. So you got to say to yourself, if I'm helping a customer every 10 minutes, and an hour goes by, 10 minutes, 10 minutes, 10 minutes, how many customers did I help in an hour? 6. And what you did is you took 60 minutes an hour, divided by 10 minutes with each customer. The rate that we just read, the mean amount of time per channel to provide the service is 10 minutes. We convert it to rate from time. So now our 2 numbers are 2.5 on the arrival, 6 on the service. Sometimes I'll write it in a fraction like that because we're heading to where you need that fraction, where you're going to use it. Everybody see that? What if I said, hey, by the way, customers are arriving every 3 minutes? How do you convert that to a rate? How many customers could arrive in an hour? 20. 60 minutes, or sometimes you forget what the division is, but if you say to yourself, if I'm helping a customer every 3 minutes, one right after another, how many would I help in 60? So you go 3, 6, 9, 12. Sounds like Sesame Street. 3, 6, 9, 12, 15, 18, 20, 1, whatever it is. You end up with 20. 60 divided by 3 would be 20 customers arriving. That's how you convert that to a rate. So remember that. When you're giving something in time, it would be much easier to convert it to rate. For both arrivals and service in the same unit of time, which in this case is hour. Now the story says the waiting cost, this is the hard part in real life, but it's given to you, is $25 per hour. So we've already come up with a solution that if somebody waits too long and they leave or they get upset, we're going to lose $25 per hour. And then it says an additional channel, the cost per channel, however many employees, each one's going to be, now remember this is pay and benefits. This may not have benefits, but if it did, this would be the total cost per employee, $16 an hour. We're given the cost per channel. We're given the cost per waiting. We know the arrival rate. We calculated and converted the service time to service rate. We have almost every number we need. Now the economic analysis is these 4 numbers. You ready? What do you think that 16 is? Cost per what? For what? Per channel. No matter if you're thinking about 2 employees, 3 employees, 4 employees, this is the cost per 1 employee or 1 channel. Times, this is K, which represents how many channels are you thinking about having. We did some calculations based on us. The problem says you're trying to figure out between 2 and 3 channels. How many should you schedule, 2 or 3? And then this number 25, what do you think that is? How much you'll lose if they walk away, called the waiting cost. So you have your cost per channel times the number of channels, plus your cost per waiting, and then here's the hard one. This is called L. Jump into the PowerPoint. This will all come together. I know I'm jumping around, but I'm going to head backwards from where we're at so this all makes sense. Find that this ends up working a little better. You ready? Here are the 6 items, and look at L. L is the one you need for economic analysis for all of those. L is the average number of orders in the system. That is your economic analysis. Your cost per channel times the number of channels. You add that to your cost per waiting times L, the average number of orders in the system. Good.
Is that always?
Always. L. No, not always that number, but it's L. This particular calculation you're seeing is if we were talking about exponential service single channel. But we're talking about exponential service multi-channel on that example problem, but I just wanted you to see what L represents. All of these, all 4 of these have these 6 items that sometimes need to be calculated, but the calculations are slightly different for each one of these, especially multi-channel, very different. The rest of them are very similar to this. So, the 6 items, you ready? 6 items for all of these is the probability of no errors in the system is at the top, almost always, but you gotta read them to make sure. Then here's the other probability. The probability an order must wait. And I want you to notice something. When you have single channel, it's 1 minus the ratio of your arrivals over your service rate. 20, in this particular example, we have arrivals at 20 an hour. We can provide service up to 30, so we're taking care of business. 20 divided by 30 is 67%. 1 minus that, there's a 33% chance of no orders in the system, and this person can twiddle their thumbs. And the opposite of that would be just your arrivals over your service without subtracting from 1. There's a 67% chance that the orders must wait, that the person providing service is busy, and the order that just arrived is going to have to wait. Now this is one of the most important probabilities. The probability an order has to wait is what businesses focus on when they have competition. They want this, like a business has lots of competition, their fear is customers waiting too long and going to the competition down the road and maybe not coming back. So they say, what do we have to do to get this as low as possible? I heard some managers say, I want this less than 5%, but more common ones are 10% when they have competition. Now, someone like Secretary of State who has no competition, they don't care what this is. What I just calculated for this one, 67%, they wouldn't say, oh, we need to add another channel. They'd say 67% chance someone's going to have to wait. And sure enough, there's probably more than a 67% chance if you've been a Secretary of State. By the way, I voted, but I didn't see the results. Do we have a new Secretary of State starting next year or the same? Nobody else knows. Wow. Wow. Am I recording this? This is a college class. Hang on. All right, just checking. Wow, you guys. I mean, you did. Someone voted, right? Well, I know. I saw you. I read him at the polls, but you don't know this who won for Secretary of State? The candidate that was challenging ran on the platform that she was going to, if you have to wait 30 minutes or more, or kick me out of office, was her thing. Did anybody hear that, or was it just me? Nobody heard that? Her slogan on her commercial was, if you elect me, you will no longer wait longer than 30 minutes. And if you wait longer than 30 minutes, you vote me out when the next election comes in 4 years, or 2 years, whatever it is. You didn't hear that one? I wonder if she was. And for someone to say, I promise you only have to wait 30 minutes. Wow, that's so the opposite of business. In real business, 30 minutes is far too long to wait. You wouldn't stay in business. That's how it is. So anyway, you ready for the story now? I want to make sure I cover everything. Oh, wait. Let's go back to our example. All right, we got how this is calculated, number of channels, waiting costs, and hours. Look at this for 2 channels. We're thinking about having 2 people do the job or 3. How many should we just realized now that we should schedule how many? How many? 2 or 3? 2. Even though a third channel will provide better customer service, lower our probability of a customer having to wait, it's possible 2 channels may already have us at that goal of a probability of a customer having to wait, and the overall cost, because of that waiting cost, did not drive the 2 channels into being more expensive than 3 channels. We're going with 2 channels. When you're evaluating economic analysis with multi-channels, it usually goes like this. Over here is because you have too few channels and that waiting cost is killing you. Over here is where you schedule too many employees, too many channels, and you're way overpaying in costs. These formulas are finding this point for you, where you have just the right amount of employees and just the right amount of low waiting to keep your overall costs as low as possible. I used to be on the, I can't remember what it's called, the board for a credit union. And this was a big deal for them because I can't remember what their shifts were, but they're open for a certain amount of hours. I believe they would figure this out for every 4 hours of every day. Meaning at a credit union, because everything's done through the computer, they can go at the end of the day and know exactly how many customers came in that day and every day before it. They know exactly what time every customer came in. And so they take that information and go, based on what's today, Wednesday. Based on a Wednesday in mid-November, for the last 10 years or 5 years, our mean amount from this time to this time, arrivals have been this many. They know exactly what the cost per channel is going to be, and they just enter in, hey, from here to here, how many should I have? And that software calculates that spot right there. There may be a question you have to fill in if the probability of a customer waiting becomes important, then a lot of companies will say, okay, that's another thing to take into consideration, but it has to, you put in the software, what's the probability goal for a customer having to wait? You'll put like 10%, which you're telling it, as long as the probability of a customer waiting is 10% or less, I want to know how many employees to put on there that will keep my overall cost as low as possible. And before that was invented, people would just wing it. Oh, we always have 6 tellers from this time to this time, without taking into consideration how many are standing there and hardly helping customers, unless they visually see it. This calculates it exactly for you. It's the right decision, so you stop wasting money. In this case, we'd go with 2 tellers. Okay, here's our first example. By the way, you're going to see these symbols. That one, I think, let's see, this one's new, and that one's Lambda, excuse me. This lambda is usually your average arrival rate. Very easy to convert a rate to time, 1 over lambda. And then here, mu is your average service rate. Convert it to time, 1 over mu. So that much over the time. You ready? This is exponential service, single channel, obviously Poisson arrival, all 4 of them are Poisson arrival. This is a trading firm, a stock exchange. They're on the floor at New York Stock Exchange. Joe Ferris works for them. He gets calls to make trades at 20 per hour. There's our arrival rate. The calls are coming in at 20 per hour. It's already a rate. You don't have to convert it. Each order received by Joe, though, he can average taking care of the call at 2 minutes. What do we got to do with that? Convert it. So 2 minutes. We had a call coming in every 2 minutes, but we're taking it every 2 minutes for 60 minutes. We all have been how many customers? 30. There's our service rate. So I'll add a 20 over 30. In a single channel system, you can never have the number of service rate equal or larger than the arrival rate. It is unsolvable, and your customer line will increase exponentially the longer the day goes. And your software and Excel will say unsolvable. This can't be done. Your service rate has to be larger than your arrival rate for single channel. Multi-channel, this could be 60 and 20 because 60 and 20. 60 arrival, 20 service, but the 20 service is for each channel. So if it's multi-channel, you have to have at least 4 channels, right? Because 3 channels would be 60 over 60. You never change the arrival rate and service rate. You never change it no matter how many channels you have. Always use whatever it is for 1 channel. When you tell how many channels, it'll say how many channels. You say 2, 3, 4, it will take that into consideration. I've had many students say, oh, 20, let's say this is 60 arrivals over 30 service, but there's 3 channels. They'll multiply the service by 3 and put 60 over 90, leave it at the 30, and then there'll be a question how many channels. You say 3, it will take care of it for you. You're doing an overkill by changing that. It thinks now 3 times 90. So here's our thing, 20 arrivals, 30 service. You ready? Now we're skipping slides 12 through a few because that's the probabilities of just arrivals, the probabilities of just service is of these next few slides. We're going to come back to those if we have time on next Monday. Skipping that, and we'll just skipping that. So we're skipping all the way to past slide 19 to slide 20. But you know what? I'm skipping past 20. I'm skipping past all of these. We're going right to this one. You ready? Here's what you were told. They arrive 20 per hour. Calls are being taken, can be handled every 2 minutes. We converted to 30 an hour. We put arrivals 20, service 30. What's the probabilities of no orders in the system? 1 minus your arrivals divided by service. 20 divided by 30 is 67%. 1 minus, there's a 33% chance of no orders in the system, and Joe gets to take a break. Now, these 2 are average numbers. These 2 are average time. The same 6 for all of these, okay? Average numbers are pretty easy. Average time, you've got to take into consideration that this average time is telling you what portion of the unit of time that the arrivals and the service represent. That's 20 and 30 per what? Hour. So this average time and average time are the portion of an hour. You're going to be asked to convert it to minutes. So if it ends up being, what's the number 6? Average, 7. Average time and order waits. And you calculate it to be 0.24. What does that mean? Well, you said 20 and 30 are per hour. So that's 24% of an hour. How many minutes in an hour? There's the number of minutes that that's representing. This is also, these are the only 2 that this happens with, because they're a portion of the time of whatever those are representing. If these are 20 per minute and 30 per minute, this is the portion of minutes that the average time would be. Get it? So here we go. Probability of orders, average number of orders waiting, average number of orders in the system, average time in order waits, average time in orders in the system, probability and order must wait. Two probabilities, two average numbers, two average time. The formulas start to get a little, they're really pretty basic and easy. We did the probability of no orders in the system. Average number of orders waiting is where you're taking your arrivals and squaring. So 20 squared. Divided by, parentheses, your service times, parentheses, service minus arrival. 30 per hour minus 20 per hour is 10 per hour. Times 30 per hour is 300. Divided into 20 squared, 400. 400 divided by 300. There's your denominator. Divided into 20, I'm sorry, that wasn't 20 squared. That's 20 squared. So let me do this again. 30 minus 20 is 10. 10 times 30 is 300. 300 divided into 400. As they say there. There's 1 and 1/3, or whatever you want to put, 1 point, whatever. So there, you just calculate the average number of orders waiting. Now, here is the important one. Average number of orders in the system. And the reason this is important is because this is exactly what you need to do your economic analysis. If a question is asking about an economic analysis, but is not asking about average time of order waits, average time of order in the system, probability and order must wait, you don't need to even do these three. You just need to get to this point so you can do your economic analysis. The waiting cost per unit of time will be given. The cost per channel will be given. The number of channels will be given. This is the only thing you'd have to calculate to do the economic analysis. You for sure have at least one or more problems where that's all it's asking for. Would you go with this hire or this hire? Or would you go with 2 or 3 for this next shift? Or would you go with 3 or 4? And all you got to get to is the L and then do the economic analysis. There may be a problem that is asking for this amount of time. So, to get, by the way, this average number of orders in the system is taking the average number of orders waiting from H5, add the proportion of arrivals divided by service. So this would be add 0.666, 2/3, to whatever that equals. This one is taking H5 again, whatever the average number of orders waiting, divide by the arrival rate. This one is taking the average time an order has to wait, add to it 1 over the service rate. 1 over 30 gets added to that. And then this one is just your arrival divided by service. They're not that hard. And if you want to set this up, they're giving you exactly how to set it up on Excel, and you're using Excel to do this, and you want to send me the Excel spreadsheet at the end of the test, get my attention, we'll turn on the internet, you can send me that. You've got to have the formulas, I got to see what you entered. That could be your work, or maybe at least transfer it to paper and send me the Excel spreadsheet, at least showing me what you did and how you get your answer. But you can have all 4 of these, if we make it through all 4, on an Excel spreadsheet if you want. Does that sound fair?
So essentially, once we find your hour rate and exponential,
Everything's calculated
everything's done.
for this one. It's not true for the next one. All right? For exponential service single channel, all you need is arrival service and done. You have all your calculations. Someone had their hand. Who was it? Jake was it? Who had their hand? Oh, I did? Okay. All right. Multi-channel. Jump to that. By the way, here's our answers. 33%, 67%. This is 1.33. And this was this plus arrivals over service, so 1.33 plus 0.67 is 2. 0.067. What would I multiply that by to figure out the real time in minutes? 60. This 0.10 times 60 minutes. Because it will say, what's the question? And by the way, I'm not going to try to trick you. I'm going to use almost these exact words. Not exact, but almost. This question might say, we have 20 arrival, there's 30 service rate going on. What's the average time an order might be in the system in minutes? So you're going to calculate and get 0.10, but then you multiply it times 60 minutes to convert it. Only on the time do you have that little extra step, okay? Let's get to multi-channel. This is the formula for that first calculation of the average, the probability of a unit would have, I forget what the first one is. Probability of no units in the system. Probability of no units in the system for multi-channel is this. Okay? We'll show you a shortcut. Are you staring at anybody? Can't believe it. You gotta get my book out. Shortcut. We're going to page 519. This is for multi-channel exponential service only, which is the only multi-channel you're going to learn this semester, right? In this class. And instead of doing that long calculation, which by the way, on bottom of page 517, there it is again. Here are the 6 calculations, the same 6, but different calculations for multi-channel exponential service, like we had for single channel, we had 6. But that first one takes so long to calculate that you jump to this page. And I'll make sure and give you one that makes sense on this page, at least somewhat sense. And this page says if you have a multi-channel, just take your arrival rate. So if you have time, you got to convert to rate. Divide it by your service rate. And find that number on this column, or at least close to that number. Then go across to where, is it 2 channels, 3 channels, 4 channels, or 5 channels, and you found your P sub O, which is your probabilities of no units in the system. Just going on this, you don't have to calculate that whole thing. So, are you ready? Joe is starting to get more calls because the company did some advertising. So the arrivals are not coming in at 20 anymore. They're increasing the arrivals by 50%. So arrivals now are at, help me out, 30. But no matter how many Joes we have, each Joe can only provide service at 30. We don't change that number, no matter how many Joes we have. I can't emphasize that enough. It's such a common mistake I see every semester. So we're at a 30-30 for each channel, right? We go to 30 divided by 30 is 1. The P sub O, the probability of no units in the system for 2 channels, whoops, did I go straight across? Is that it? Am I straight across? I'm too close, am I? 33% chance. For 3 channels, 36% chance. Is that right? For 4 channels, a little more than 36, almost 37% chance. Am I straight across? Yeah. Am I? Okay. And look at how adding another channel barely affects that percent of no units in the system. So there it is. Your P sub O is right there on the chart. Real quick. Hey, we've got an arrival rate of 5 and a service rate of 8. I'm making it up. Someone calculate that for me. 5 divided by 8. These are both the rates. Help me out. 65%? 625. 625. We're going right there between 6.0 and 625, and we're wanting to get the P sub O for 2 channels. Now, if you use the 6.0, which is what, 0.5385, is that correct? Anybody, 53? Or if you, that's, you said 0.625? Yeah. So where's the 0.65? So it's right there between 0.5385 and 0.5094. I'll be so happy if you use either one of those. But if you're my A students, I want you to find the number, estimate the number between the two, because 0.625 is right between the 0.60 and the 0.65. So you might use, hit me, you might use 0.5, come on my A students, where are they? Huh? Paige, you're going to get this? 0.51. 0.51, she says. Let me look here. We had a choice between, no, 0.53 and 0.56 are your 2 numbers. Give me another number. Kyle?
No, you said 0.53 and 0.50.
Ah, well, I got it back up now. Thank you. I don't mind being corrected. I appreciate it. Thank you very much. 0.61, I love it. We had, what are we between? 0.51, excuse me. 0.5385 and 0.5094. I'd almost go 0.52, right? Anyway, either one of those numbers I would be happy. There's how you get your first calculation, the probability. The second calculation, I'm going to the book. Second calculation, because of multi-channel, is a little more difficult than with single channel. Here's what we just did, and we have to have that for the next calculation on multi-channel. So it's right there. You multiply by 0.52. Is that what we agreed on? 5152? That's that. Now I want to explain the rest of this because it's not that hard. The arrival rate, we said, is now going from 20 to 30. Joe still only can handle 30 at a time, and we're looking at just, this is all based on what one channel can handle. So that symbol's the arrival rate, that was the service rate, and these are the only numbers you're using other than the K, which is the number of channels. And we're right now figuring out 2 channels. So I have 30 divided by 30 squared times 30 times 30. 2, the number of channels we're evaluating, minus 1. Uh-oh. 2 minus 1 factorial. Some people haven't seen factorial in years. What? What? You ready? I'm going to refresh your memory real quick on factorial. 3 factorial. 3 times 2 times 1. 4 factorial. 4 times 3 times 2 times 1. It's every number, whatever's being factorial, times all the way down to 1 for whatever number you're factorial finding. 6 factorial. 6 times 5 times 4 times 3 times 2 times 1. So it's however many service channels minus 1. That's, so in our case, 2 minus 1 is 1. 1 factorial equals 1. So 2 minus 1 factorial is a 1. K, 2 channels, times our, is that service or arrival? Service rate, so 2 times 30, minus our arrival rate, which is 30, then take that whole thing and square it, then multiply it times the 1, or whatever the factorial is you calculate. Divide that into your numerator, last, multiply times what we just found on that chart. That's just to get the average number of units weighted. You take the average number of units weighting and look at how this calculation is the exact same as single channel, very easy. Once you get past these two, things in fact is semi-easy. Here is whatever we calculated there, plus the arrival divided by service, which is 30 over 30, which is 1. We have L now. We can do our economic analysis. Well, we have still 3 more calculations we may have to do, but if all it's asking for economic analysis, we can stop right there. The other 3 we might have to do for multi-channel, which are very easy, once we got past the beginning there. The average time a unit spends waiting, there it is, the L sub Q over the arrival rate. The average time the unit spends in the system, same as single channel. The probability an arriving unit has to wait is a long formula. I probably won't be asking for this. But if you notice, we already have that, just in case, 1 over the number of channels factorial. We're not subtracting 1, so this would be 2 times 1, which is 2. Then arrivals divided by the service to the exponent of the number of channels. The number of channels times the service rate divided by the number of channels times the service rate minus the arrival rate. Take all of this and multiply it, then multiply it times that thing we got off the chart, that P sub O, the very first step we took for multi-channel. You can solve these. They just look long, but they're actually really pretty easy. Here, in almost all these, you're using the arrival rate, the service rate, and the number of channels. And that's all you need, is just plug them into the right formula. Here it is on the slides. What time is this class over? Gosh, this word, you guys are packing up on it. All right, hang on. Now this one's kind of messy, and I don't even like it at all. And so I'm really recommending, if you recognize something as multi-channel, and it should be easy, the only one, I would go to those pages that we've just been talking about. Page 417, 418, and 419. Very clear, you know exactly. I said 4, sorry. 517, 518, 519, thank you. All right? You can now do multi-channel. Let's say we got to the L. Let's see what our L is here. 1.33. There's a waiting cost. We calculate that the waiting cost is $20 per hour. What does that get multiplied? The waiting cost gets multiplied times the number of channels? Not all at once. What do I multiply in economic analysis the waiting cost by per unit of time? Like per hour, huh? No, you may be right. I didn't hear you. Total, it is total something. Not the total cost. Well, that's what we're calculating, total cost, almost. The total, what is it? Maybe it isn't total. L. I can't emphasize it any more than I have to. L. The average number of units in the system is what you're multiplying your waiting cost by. Whatever that is. Plus, the story says every person that we have do this job is going to make about $16 an hour. And what do I multiply that by? The what? I can't hear you. You're probably right, but I can't hear you. K, which is?
Number of channels.
Number of channels. Which in this case, we're talking about 2 channels. So once we got to L, we can figure out what that equals. Now, the question is going to say, what about 3 channels? We go back, because you're going to have a different L. But it's still $20 waiting cost. It's still $16 per channel. But this time there's 3 channels and a different L. A different average number of orders in the system, because you're going to have a different calculations here, because your K now is 3, not 2 anymore. When you get to L, it's going to be slightly different, and you're going to get an ending calculation, and it's all about, does the waiting cost or the cost per channel end up causing this to be more expensive, which will be our optimal solution, having 2 channels or 3 channels. And that, showing this work, getting to that, answer that question in the economic analysis, is what that problem's all about. And that's how it's really done in the real world. You've got to get to that economic analysis to figure out what the best economic decision is. 2, should we have 2, or is 3 an overkill, or is 2 not enough? All right? You ready? Now we're going to the software. Management scientists. Which module should we use? Number 9, waiting lines? Sounds good. There we go. File, new. Which one? The one we just talked about was multi-channel. Let's do the single channel now. No, okay, single channel. Single channel, we had 20 arriving. You can handle it every 2 minutes, so that was 30 service rates. That sound right? So we're going Poisson arrival. By the way, let's read these. Poisson arrival, exponential service. It doesn't say whether it's single channel or multi-channel. The next one will say, and how many channels? 1, 2, 3. You put a 1, that means single channel. 2 or more means multi. This is the one we're doing. Here's arbitrary. Poisson arrival, arbitrary. This is the one that the service will include a standard deviation. You know to click there if you're using the software to confirm your answer or whatever. Now, deterministic service is the same. That word deterministic means constant. So that one that we're going to learn next week for constant service is that third one down. We're not doing arbitrary. We're not with no waiting line. We're not doing finite population exponential service. Those last 2 we're not doing in this class. There's 2 exponential service, single channel and exponential, which you click here. There's your arbitrary, and there's your constant, the first 3. We're going to exponential. How many channels? We're going to do the 1 channel. The arrival rate was 20 per hour. The service rate was 30 per hour. And we can stop right there and get our 6 numbers. Right now we can get our 6 numbers. Probability, average number, average time, probability. Let's do an economic analysis. We'll click here. Hey, does it tell us, I'll go to the bottom one, cost per channel? If we went into the story a little more, it's going to tell us that if we have another Joe doing it, I think it says $20. Let's just use 25. It's the one realistic. Now this one should say cost of waiting per period. It doesn't have the word waiting there, but this is really what it's asking for. That waiting cost that's given to you. And let's pretend the waiting cost, I think the one we've been using is 25 an hour, right? Let's use 25 an hour. That's the same cost. Let's use something else. Let's use 19. $19 an hour waiting, $25 an hour to add another channel. We're looking at just one channel. So this will give us the cost per unit of time, which this is 20 per hour, 30 per hour. So our total cost for a waiting cost with our channel cost per 1 unit of time. Here we go. The probability of no use in the system, 33%. The average number of units waiting, 1.333. Same thing on the PowerPoint, all these numbers. The average number of units in the system, 2. The average time the unit spends waiting, 0.0667 of an hour. That's 20 per hour and 30 per hour that we entered. Average time unit spends in the system, 0.10 of an hour. You got it. The probability that an arriving unit has to wait, oh my God, 67% chance. But this type of business, people expect to wait maybe. That's why it's so high. The total cost per time period, in this case per hour, because we entered at 20 and 30 per hour, $63. That's the person in the waiting. When you have such a high probability of someone waiting, that drives that up. And that's why that's so high. What if we have a second channel? Go ahead.
What do you do if you have multiple channels, but each person makes a different wage?
For this, we're not going there. It's a much bigger formula. But for this, we would use the average wage. So if one's making 20 and the other one's 18, we're going to use 19. For this. I wouldn't give you a problem like that, by the way. I'm not going to try to trick you guys. I know this is going to be hard enough. So when I give you the cost per channel, it's no matter how many people we have there, it's the same cost. So watch what happens when I switch this to multi-channel. What I want to point out is I'm not going to change the service rate even though we have more than one employee providing the service. It's what each employee provides. And what if the 2 employees have different service rates? What about that? You would use the average service rate in this case then. Okay? But I wouldn't give you a problem where you have to average it. I'm going to give you the service rate per channel, period. So let's edit this. We're going to go now, we're going to have 2 Joes. But what does change is the arrival, and this is what led us to possibly needing a second person. We're not having calls coming in at 20 per hour now, they're coming in how fast? Remember, was it 30? Was it time? They think it's going to increase by 50%, so we're looking at 30 per hour. But the service rate, notice it says per channel, is still 30. Even though one person can take every 2 minutes, and the other one every 2 minutes, it's per channel. Cost of waiting is still $19. The cost per channel is still $25. We didn't change anything but the number of channels and the arrival. The only thing we changed. Go ahead, Mike.
So if the number of channels is 1, it could be 30 over 30, right?
That's right.
Okay.
Watch what happens. You ready?
Okay.
Can't happen. Now let's see why. The arrival rate must be less than 30, or the waiting line will roll without limits. Or just say, or it'll be like you're at the Secretary of State. That's what she said. I mean, I don't know if every state's like that. Are you ready? Now I'm going to go to 2. And the only thing we changed was the arrival, because the story says we've done some advertising and our arrivals, calls are coming in 50% more. So 30, 30, and 2. Nothing else changes. What was the cost with one person per hour? $63 or something like that? Yeah. Let's see if this goes. We have more arrivals, but with 2 people, same waiting cost, same cost per channel. Did we save money or does this cost us more money? It costs us more money. It is. But we couldn't handle the calls unless we got a second person. Wait, maybe the waiting cost is still so affecting us that maybe we need a 3rd person. Even though the arrivals aren't increasing, maybe we just want to lower the probability of someone having to wait. Let's see if we save some money, because that would lower the waiting cost, but the waiting cost would have to lower enough to justify the extra, how much per person, 25? The extra cost of another channel. By the way, our probability of a customer having to wait was 67%. By adding a second person, even though we have arrivals coming in faster, What's the probability of a customer having to wait now? Yeah, that's still, in real business, that's still not acceptable if you got a lot of competition. That's not acceptable. You gotta say, okay, I'm gonna bite the bullet, and I'm bringing in a fourth person, or a third person, excuse me. So we go edit, nothing else is changing, we're just going to a third person and figuring out if we save money or it costs more money. Because our probability of someone having to wait is gonna come way down now, because the arrivals didn't change. Probability of someone having to wait is now what? Yeah, about 9%. Our cost went up or down? Up. Now, you gotta ask yourself, is it worth this additional cost? What was the previous one? It was 63 to 75 to 94. Is it worth this additional money per hour to have that? And if a company has competition, their answer is almost always yes. Because 75 to 94 per hour, to not have a customer leave me and go spend the average, our business, the average, on average, every customer spends, $60. So to have that customer leave and not come here anymore to spend their $60, it's worth the 75 to, what is that, almost $19 per hour additional cost to bring this down. This is very good. Almost every company's happy with 10% or less, unless they have extreme competition. I've seen a lot of companies say, I want 5% or less chance of someone having to wait. All right, you see how this is used? We only talked about 2 of them. We got 2 more to talk about next week. And if we make it, we'll have these 2 to talk about. I don't think we're going to make it that far. I think we're going to focus on these and more economic analysis. And that's what will be on the quiz and not these, I think. We'll know as of Monday of next week. Have a great weekend.